Right now, somewhere on this planet, there is a physicist staring at a chalkboard covered in equations. Those equations describe something nobody has ever seen, something nobody has ever touched, something nobody has ever measured. And yet, this physicist has dedicated their entire life to understanding it. They wake up thinking about it. They fall asleep dreaming about it. They have spent decades working on a single idea, a single theory, a theory that promises to explain everything in the universe, every particle, every force, every moment from the beginning of time to the end of time. And here is the thing that should keep you up at night. After more than 50 years of work, after thousands of the most brilliant minds in human history have poured their lives into this theory, we still have zero direct proof that it is true. None, not a single experiment has confirmed it. Not a single observation has verified it. We are talking about string theory. And today, we are going to ask the question that very few people are willing to ask out loud. What would it actually take to prove it? Is it even possible? Or are we chasing a beautiful ghost? Think about that for a moment. We live in an age where we can detect gravitational waves from two black holes colliding 1 billion light years away. We can photograph the shadow of a black hole. We can measure the afterglow of the Big Bang with incredible precision. We can smash particles together at nearly the speed of light and discover new fundamental building blocks of nature. We have done extraordinary things. And yet, when it comes to string theory, the theory that is supposed to be the ultimate explanation of reality, we are stuck. We cannot test it. We cannot verify it. We cannot even agree on what it predicts. So what is going on? Is string theory the greatest intellectual achievement in human history, or is it the greatest waste of time? Is it a revolutionary truth that we simply do not have the tools to confirm yet? Or is it a beautiful mathematical fantasy that has nothing to do with the real world? And perhaps the most unsettling question of all. Is it possible that the proof has been hiding in plain sight this whole time, and we have simply been looking in the wrong place? Before we go any further, let me tell you some things that will genuinely shock you. The energy required to directly observe a vibrating string, the fundamental object in string theory, is roughly 1 quadrillion times greater than what the most powerful particle accelerator on Earth can produce. To put that in perspective, the Large Hadron Collider near Geneva, the most powerful machine ever built by humans, would need to be scaled up by a factor of 1,000,000 billion. A particle accelerator that could reach these energies would need to be roughly the size of our entire Milky Way galaxy. That is not a joke. That is actual physics. Here is another one. String theory does not describe just one universe. It describes a landscape of possible universes, and the number of possibilities is 10 to the power of 500. That is a 1 followed by 500 zeros. To give you a sense of how absurd that number is, the total number of atoms in the observable universe is roughly 10 to the power of 80. The number of possible string theory universes has more digits than there are atoms in everything we can see. Our universe, if string theory is right, is just 1 grain of sand on a beach that stretches beyond imagination. And here is something that might be the most surprising of all. Despite having no direct proof, string theory has already produced one of the most remarkable results in the history of physics. In 1996, 2 physicists used string theory to calculate the entropy of a black hole from first principles, and they got the exact answer that had been predicted decades earlier. Not approximately. Exactly, that result made even the skeptics pause. And in recent years, physicists have used the mathematical tools of string theory to resolve one of the deepest paradoxes in physics, the black hole information paradox. Something that Stephen Hawking himself struggled with for 30 years. So we are dealing with something genuinely strange here. A theory with no direct proof, but with results that are almost too perfect to be a coincidence. A theory that seems to know something about the universe that we have not yet figured out how to verify. Today, we are going to go deep, really deep. We are going to start from the very beginning, from the crisis in physics that made string theory necessary. We are going to understand what strings actually are, not the simplified version, the real thing. We are going to explore every single experiment and observation that could potentially prove or disprove this theory. We are going to hear from the greatest minds on both sides of the debate. And by the end, we are going to have an honest, clear-eyed answer to our question. What would it actually take to prove string theory? This is not going to be a quick overview. This is the complete story. So settle in, get comfortable, and prepare to have your understanding of reality fundamentally challenged. And before we dive in, if you are the kind of person who genuinely loves exploring the deepest mysteries of the universe, if these are the questions that keep your brain buzzing at 3 a.m, then you are exactly where you need to be. Take a second to subscribe to this channel. Hit that like button because it genuinely helps more people find videos like this. And drop a comment right now telling me your gut feeling. Do you think string theory is real? I want to know what you think before we begin. Let us see where the community stands. And then, by the end of this video, come back to the comments and tell me if your mind has changed. Alright, let us begin. To understand string theory, you first need to understand the crisis that gave birth to it. And that crisis is one of the most profound problems in all of science. It is the problem of two theories that both work perfectly, but that fundamentally contradict each other. The first theory is general relativity, created by Albert Einstein in 1915. General relativity describes gravity. It tells us that massive objects like stars, planets, and black holes curve the fabric of space-time, and that this curvature is what we experience as gravity. It is not a force pulling you down. It is the shape of space-time itself guiding your motion. General relativity has been tested to extraordinary precision. It predicted the bending of light around the sun, which was confirmed during a solar eclipse in 1919. It predicted gravitational time dilation, which we now account for in GPS satellites every single day. It predicted gravitational waves, ripples in the fabric of space-time itself, which were directly detected by LIGO in 2015, a full century after Einstein predicted them. General relativity works. It works beautifully. It governs the behavior of everything large, from the motion of planets to the expansion of the universe to the behavior of black holes. The second theory is quantum mechanics, which emerged in the 1920s through the work of physicists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and many others. Quantum mechanics describes the behavior of the very small, atoms, electrons, photons, quarks, and it is bizarre. It tells us that particles can be in two places at once, that the act of observing something changes its behavior, that there is a fundamental limit to how precisely we can know certain properties of a particle. Quantum mechanics is not intuitive. It is deeply strange. But like general relativity, it has been tested to extraordinary precision. The predictions of quantum electrodynamics, the quantum theory of light and matter, have been confirmed to more than 10 decimal places. It is the most precisely tested theory in all of science. Quantum mechanics is the foundation of modern technology. Your smartphone, your computer, medical imaging, lasers, semiconductors, all of it depends on quantum mechanics being true. So we have two theories. General relativity governs the large. Quantum mechanics governs the small. Both have been tested beyond any reasonable doubt. Both work spectacularly well in their own domain. And here is the crisis. When you try to combine them, when you try to create a single theory that includes both gravity and quantum mechanics, the mathematics breaks down. You do not get a sensible answer. You get infinities. You get nonsensical predictions. The equations literally blow up. Imagine you have two instruction manuals for building something. One manual tells you exactly how to build a skyscraper. Every measurement is perfect. Every instruction is precise. The other manual tells you exactly how to build a microchip. Again, perfect in every detail. But when you try to combine the two manuals, when you try to build a skyscraper with a microchip inside it, using both manuals simultaneously, the instructions suddenly start telling you to divide by 0. They contradict each other. They produce gibberish. That is the situation in physics. General relativity and quantum mechanics are individually perfect, but together they are incompatible. Now, you might ask, does this actually matter? If each theory works in its own domain, why do we need to combine them? The answer is that there are places in the universe where both theories must apply simultaneously. There are situations where something is both very massive and very small. And in those situations, we need a theory that combines both gravity and quantum mechanics. A theory of quantum gravity. The most obvious example is a black hole. At the center of a black hole, according to general relativity, all the mass is compressed into an infinitely small, infinitely dense point called a singularity. But infinitely small means we are in the quantum realm. We need quantum mechanics to describe what happens at that point. And when we try to apply quantum mechanics to the singularity, the math breaks down. We get infinities. We get nonsense. We literally do not know what happens at the center of a black hole because our two best theories cannot work together there. The other example is the Big Bang, at the very first instant of the universe. All the matter and energy that exists today was compressed into an unimaginably small, unimaginably hot, unimaginably dense state. That state was both gravitationally extreme, requiring general relativity, and microscopically tiny, requiring quantum mechanics. To understand the very first moment of the universe, the moment of creation itself, we need a theory of quantum gravity. Without it, we literally cannot describe how the universe began. This is the crisis. This is the fundamental problem that has haunted physics for nearly a century. We need a theory that combines gravity and quantum mechanics, and we do not have one. Or rather, we did not have one, until string theory came along and said maybe I am the answer. But before we get to string theory itself, we need to understand one more piece of the puzzle. We need to understand the standard model of particle physics, because it tells us what we already know about the fundamental building blocks of nature, and more importantly, what we do not know. The Standard Model is one of the most successful scientific theories ever created. It describes all the known fundamental particles and 3 of the 4 fundamental forces of nature. Let me walk you through it. First, the particles. Everything in the universe, every star, every planet, every person, every atom, is made of a relatively small number of fundamental building blocks. There are 12 matter particles divided into two families. The first family is the quarks. There are 6 types of quarks, called up, down, charm, strange, top, and bottom. The up and down quarks are the ones that make up protons and neutrons, which in turn make up the nuclei of atoms. The other 4 quarks are heavier and less stable, and they only appear in high-energy environments like particle accelerators or the early universe. The second family of matter particles is the leptons. There are also 6 types of leptons. The most familiar is the electron, the particle that orbits the nucleus of an atom and is responsible for electricity and chemistry. There is also the muon and the tau, which are heavier versions of the electron. And there are 3 types of neutrinos, one associated with each of the charged leptons. Neutrinos are incredibly light, possibly almost massless, and they barely interact with anything. Billions of neutrinos from the sun pass through your body every second, and you never notice. These 12 matter particles are organized into 3 generations. The first generation contains the up quark, the down quark, the electron, and the electron neutrino. These are the lightest and most stable particles, and they make up essentially all of ordinary matter. The second and third generations are heavier copies that quickly decay into first-generation particles. Then there are the force-carrying particles, called bosons. In quantum mechanics, forces are transmitted by exchanging particles. The electromagnetic force, which governs electricity, magnetism, light, and chemistry, is carried by the photon. The strong nuclear force, which holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei, is carried by particles called gluons. There are 8 types of gluons. The weak nuclear force, which is responsible for certain types of radioactive decay, and plays a crucial role in the nuclear reactions that power the sun, is carried by 3 particles called the W+, W-, and Z bosons. And finally, there is the Higgs boson, which was predicted in 1964 by Peter Higgs and several other physicists, and finally discovered at the Large Hadron Collider in 2012, almost half a century later. The Higgs boson is associated with the Higgs field, which permeates all of space and gives mass to many of the fundamental particles. That is the Standard Model. 17 fundamental particles, 3 forces, and it works spectacularly well. The Standard Model has predicted the results of thousands of experiments with incredible accuracy. The discovery of the Higgs boson was its crowning achievement, a prediction made decades in advance and confirmed exactly as expected. But the Standard Model has problems. Serious problems. And these problems are what drive physicists to look for something deeper. The first and most glaring problem is that the Standard Model does not include gravity. It describes 3 of the 4 fundamental forces, but gravity is completely absent. There is no graviton in the Standard Model. The Standard Model simply has nothing to say about the force that governs the large-scale structure of the universe. This is a profound failure for a theory that is supposed to describe the fundamental laws of nature. The second problem is dark matter. Astronomical observations tell us that roughly 27% of the universe is made of dark matter, a mysterious substance that has gravitational effects but does not interact with light or any of the forces in the Standard Model. We can see its gravitational influence on galaxies, on galaxy clusters, on the cosmic microwave background. But we have no idea what it is. The Standard Model has no particle that could be dark matter. The third problem is dark energy. Roughly 68% of the universe is made of dark energy, a mysterious form of energy that is causing the expansion of the universe to accelerate. The Standard Model has no explanation for dark energy. In fact, when physicists try to calculate the expected amount of dark energy using quantum mechanics, they get an answer that is roughly 120 orders of magnitude larger than what we observe. That is the worst prediction in the history of science. The fourth problem is that the Standard Model has roughly 20 free parameters. Numbers like the masses of the particles and the strengths of the forces that the theory cannot predict. They have to be measured experimentally and then put into the theory by hand. Why does the electron have the mass it has? Why is the strong force the strength it is? The Standard Model cannot tell us. These numbers appear to be arbitrary, and yet, if you change any of them even slightly, the universe would be radically different. Stars might not form. Atoms might not be stable. Life would be impossible. This apparent fine-tuning cries out for an explanation, and the Standard Model cannot provide one. The fifth problem is the hierarchy problem. The Higgs boson has a mass of about 125 billion electron volts. According to quantum mechanics, the Higgs boson should receive enormous quantum corrections to its mass from virtual particles. Corrections that would push its mass up to the Planck scale, roughly 10 to the power of 19 billion electron volts. That is about 10 quadrillion times heavier than what we observe. For the Higgs to have its observed mass, there must be an incredible cancellation between the bare mass and the quantum corrections, a cancellation precise to about 1 part in 10 to the power of 32. This seems absurdly unlikely, and it suggests that something is going on that we do not understand. So the Standard Model, despite its spectacular successes, is clearly incomplete. It does not include gravity. It does not explain dark matter or dark energy. It has arbitrary constants that it cannot predict. And it has the hierarchy problem. Something deeper is needed. Something that goes beyond the Standard Model and resolves these mysteries. And this is where string theory enters the story. But the way it entered is one of the most surprising and unexpected episodes in the history of science. Because string theory was not designed to solve any of these problems. It was discovered completely by accident. The year was 1968. The place was CERN, the European Organization for Nuclear Research. In Geneva, Switzerland, a young Italian physicist named Gabriele Veneziano was working on a problem that had nothing to do with quantum gravity or the theory of everything. He was trying to understand the strong nuclear force, the force that holds atomic nuclei together. At the time, physicists were struggling to describe how particles called hadrons, which include protons and neutrons, scatter off each other in high-energy collisions. Veneziano was looking for a mathematical formula that could describe the patterns seen in these scattering experiments. And he found something remarkable. An old mathematical function, the Euler beta function, originally studied by the Swiss mathematician Leonhard Euler in the 18th century, perfectly described the data. Veneziano did not know why it worked. He just knew that it did. The formula captured the scattering patterns beautifully. 2 years later, in 1970, 3 physicists working independently, Yuichiro Nambu in Chicago, Holger Beck-Nielsen in Copenhagen, and Leonard Susskind at Stanford, made a stunning realization. They figured out what Veneziano's formula was actually describing. It was not describing point-like particles bouncing off each other. It was describing tiny one-dimensional objects, like incredibly small rubber bands, vibrating and interacting. These objects were strings. This was the birth of string theory, though at the time nobody called it that. It was called the dual resonance model, and it was meant to be a theory of the strong nuclear force. The idea was that hadrons were not just point-like particles, but were actually connected by tiny strings. When you pulled two quarks apart, the string between them would stretch, storing energy, much like stretching a rubber band. If you pulled hard enough, the string would snap, but instead of breaking cleanly, it would create new quark-antiquark pairs at the broken ends, producing new hadrons. This picture actually explained a lot about the strong force. But there were problems. Serious problems. The first problem was that this early string theory only worked mathematically in 26 dimensions of spacetime. 26. Not the 3 space dimensions and 1 time dimension that we actually live in, but 26. This seemed absurd. The second problem was even worse. The theory predicted a particle that traveled faster than the speed of light, a tachyon. Tachyons create all sorts of logical paradoxes and violate the fundamental principles of Einstein's relativity. A theory that predicts tachyons is generally considered to be sick. The third problem, and the one that ultimately killed string theory as a theory of the strong force, was that it predicted a massless particle with a property called spin 2. No such particle existed in the world of hadrons and the strong force. This massless spin 2 particle was an embarrassment, an unwanted prediction that seemed to have nothing to do with nuclear physics. Meanwhile, in the early 1970s, a different theory of the strong force emerged, one that worked spectacularly well. It was called quantum chromodynamics, or QCD. QCD described the strong force in terms of quarks and gluons interacting according to the rules of quantum field theory. It was tested against experiments, and it worked. QCD quickly replaced the string model as the accepted theory of the strong force. String theory, it seemed, was dead. A beautiful mathematical curiosity that described the wrong physics. Most physicists abandoned it and moved on, but a few stubborn individuals refused to give up. And they noticed something that changed everything. Remember that unwanted massless spin 2 particle? The one that did not match any known hadron? Some physicists, including John Schwartz at Caltech and Joel Shirk in Paris, realized that this particle matched the description of something else entirely. It matched the graviton, the hypothetical particle that would carry the force of gravity in a quantum theory. Think about the magnitude of this realization. String theory was never meant to describe gravity. It was supposed to be a theory of the strong nuclear force, but buried in its mathematics was a prediction of a particle that looked exactly like the carrier of gravity. It was as if you were digging in your backyard looking for a water pipe and accidentally struck gold. In 1974, Schwartz and Shirk proposed something radical. They said that string theory should be reinterpreted not as a theory of the strong force, but as a theory of quantum gravity. The strings were not the size of protons, as originally imagined. They were far, far smaller, roughly the Planck length, which is about 10 to the minus 35 meters. At that incredibly tiny scale, the strings would naturally produce gravity and all the other forces of nature. This was an extraordinary claim. But almost nobody listened. The physics community was focused on the Standard Model, which was experiencing triumph after triumph. The idea that gravity could be described by tiny vibrating strings seemed outlandish. Throughout the late 1970s, string theory was kept alive by a tiny group of dedicated physicists, no more than a handful of people in the entire world. What kept them going was the mathematics. The mathematics of string theory was extraordinarily beautiful and surprisingly self-consistent. When you work with quantum field theories of gravity, you typically run into a fatal problem called non-renormalizability. The calculations produce infinities that cannot be tamed. But string theory, because it replaces point particles with extended strings, naturally smooths out these infinities. The strings have a finite size, and this finite size acts as a natural regulator that prevents the mathematical explosions that plague other approaches to quantum gravity. To understand why this matters, think about it this way. In the standard approach, particles are points, zero-dimensional objects with no size. When two-point particles collide, they come together at a single point in space-time. At that point, the energy density becomes infinite, and the calculations blow up. But in string theory, particles are tiny loops or segments of string. When two strings interact, they do not collide at a single point. Instead, they smoothly merge and split, spreading the interaction over a small region rather than concentrating it at a point. This smoothing is what makes string theory mathematically well-behaved where other theories fail. But the real revolution was still to come. In 1971, Pierre Ramond and separately André Neveu and John Schwartz discovered a way to incorporate a special symmetry into string theory. This symmetry is called supersymmetry, and it relates two fundamentally different types of particles: bosons, which carry forces, and fermions, which make up matter. In the standard model, bosons and fermions are completely separate. Supersymmetry says that for every boson, there is a corresponding fermion, and vice versa. Every particle has a superpartner. When supersymmetry was added to string theory, two remarkable things happened. First, the tachyon disappeared. The troublesome faster-than-light particle that had plagued the original bosonic string theory was eliminated by supersymmetry. Second, the number of required dimensions dropped from 26 to 10. Instead of needing 26 dimensions, the theory now required exactly 10 dimensions, 9 of space and 1 of time. 10 was still a lot more than 4, but it was a significant improvement. This new version was called superstring theory, and it could describe both bosons and fermions, both forces and matter, all emerging from the vibrations of a single type of fundamental object, the superstring. Let me make sure you understand how remarkable this is. In the standard model, there are 17 different fundamental particles, each with its own properties, its own mass, its own charge. They seem unrelated. There is no deep reason why the electron has the mass it has, or why there are 3 generations of quarks, or why the forces have the strengths they do. It is all just a collection of empirical facts. In string theory, all of this complexity emerges from a single entity. There is just one type of fundamental object, the string. Different vibrational patterns of the string produce different particles. One pattern vibrates in a way that looks like an electron. Another vibrates in a way that looks like a quark. Another looks like a photon. Another looks like a graviton. The diversity of nature is not fundamental. It is emergent. It comes from the different ways that a single type of string can vibrate. Think of a violin string. When you play it, it can produce many different notes. The fundamental frequency, the first harmonic, the second harmonic, and so on. Each note is just the same string vibrating in a different pattern. Now imagine that instead of producing different musical notes, the string produces different particles. The universe is like a symphony orchestra, but instead of many different instruments, there is just one instrument, the string, playing an incredibly complex piece of music that we experience as reality. This is an astonishingly elegant idea. From one simple object, all the complexity of the universe could potentially emerge. But elegance alone does not make a theory true. And string theory still had that nagging problem, the extra dimensions. The idea of extra spatial dimensions is not actually as crazy as it might sound. It has a long history in physics that predates string theory by decades. In 1919, just 4 years after Einstein published general relativity, a German mathematician named Theodor Kaluza made a remarkable discovery. He took Einstein's equations and extended them to 5 dimensions instead of 4. When he did this, something magical happened. The 5-dimensional equations naturally contained not just gravity, but also electromagnetism. Maxwell's equations, which describe electric and magnetic fields, emerged automatically from the geometry of the 5th dimension. Gravity and electromagnetism, 2 seemingly unrelated forces, were unified in a single geometric framework, simply by adding 1 extra dimension. In 1926, the Swedish physicist Oskar Klein took Kaluza's idea further and asked the obvious question: if there is a 5th dimension, why can we not see it? Klein's answer was that the 5th dimension is curled up incredibly small, so small that we could never directly observe it. Think of it this way. Imagine looking at a garden hose from very far away. From a distance, it looks like a one-dimensional line. But if you look closely, you see that at every point along the line, there is a small circle. The hose is actually two-dimensional. It has length and it has a circular direction around the hose. But that circular direction is so small compared to the length that from far away, you cannot see it. Klein proposed that the fifth dimension is like the circular direction of a garden hose, but much, much smaller. It is curled up at every point in space into a tiny circle, so small that no experiment could ever detect it. The size of this circle would be roughly the Planck length, about 10 to the minus 35 meters. At scales we can access, the universe looks four-dimensional. But at incredibly tiny scales, there is an extra dimension hiding at every point in space. String theory takes this idea and runs with it. Instead of one extra dimension, string theory requires 6 extra dimensions, for a total of 10. These 6 extra dimensions are not just simple circles. They are curled up into incredibly complex geometric shapes called Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xing-Tung Yau. Calabi-Yau manifolds are 6-dimensional geometric shapes with very specific mathematical properties. They are compact, meaning they are finite in size. They have a special geometric property called Ricci flatness, which is related to Einstein's equations, and they come in an enormous variety of shapes and sizes. Each different shape would produce a different pattern of particles and forces in the 4 dimensions that we observe. The idea is that the specific Calabi-Yau manifold that our 6 extra dimensions are curled up into determines the specific particles and forces that we see in our universe. Here is where things get both exciting and deeply problematic. The reason this is exciting is that it provides a potential mechanism for explaining the apparently arbitrary features of the Standard Model. Why does the electron have the mass it has? Because of the shape of the extra dimensions. Why are there 3 generations of particles? Because of the topology of the Calabi-Yau manifold. Why do the forces have the strengths they do? Because of the geometry of the compact space. All of the seemingly random features of our universe could, in principle, be explained by the geometry of the extra dimensions. But the reason this is deeply problematic is that there are an astronomically large number of possible Calabi-Yau manifolds. Estimates suggest there are roughly 10 to the power of 500 different ways to curl up the extra dimensions. Each one would give a different version of physics, a different set of particles, a different set of forces, a different value for the cosmological constant. This collection of possibilities is called the string theory landscape. 10 to the power of 500. To say that this number is large does not do it justice. It is so large that it makes the number of atoms in the observable universe, about 10 to the 80, look like essentially zero by comparison. If string theory is right, and each of these possibilities corresponds to a real universe, then there are more possible universes than there are anything in our universe. The implications of this are staggering, and we will return to them later. But for now, let me continue the story. By the early 1980s, string theory was still a niche pursuit. Despite its mathematical beauty, despite its natural inclusion of gravity, only a small number of physicists were working on it. The mainstream physics community was focused on the Standard Model, which was racking up success after success. String theory was seen as speculative, untestable, and perhaps a dead end. That changed dramatically in 1984, in what is now called the First Superstring Revolution. The trigger was a breakthrough by Michael Green of Queen Mary College in London and John Schwartz of Caltech. They were working on a serious technical problem. Quantum theories sometimes develop mathematical inconsistencies called anomalies. An anomaly is when a symmetry that exists in the classical theory is broken by quantum effects. If a theory has anomalies, it produces contradictory or nonsensical predictions. For a quantum theory to be consistent, all anomalies must cancel. Green and Schwartz showed that in superstring theory, a miraculous cancellation of anomalies occurs. All the potential mathematical inconsistencies cancel each other out perfectly, but only if the theory has a very specific mathematical structure, specifically the gauge symmetry group SO, or E8 times E8. This was a stunning result. It meant that superstring theory was not just mathematically beautiful, but mathematically consistent. It was a genuine, anomaly-free quantum theory that included gravity. No other approach to quantum gravity could claim this. Part 2, the impact on the physics community, was immediate and dramatic. Within months, hundreds of physicists abandoned other research areas and began working on string theory. The greatest physicists of the era were drawn to it. Edward Witten, widely considered the most brilliant physicist of his generation, called string theory the most beautiful theory that had ever been discovered. He said that string theory had the remarkable property of predicting gravity, that if gravity did not already exist, string theory would have predicted it. What followed was an explosion of activity. Between 1984 and 1986, physicists discovered that there were not one but 5 distinct versions of superstring theory. Let me describe each one. Type 1 string theory contains both open strings which have 2 endpoints and closed strings which form loops. It has the gauge symmetry SO and can naturally accommodate gauge fields similar to those in the Standard Model. Type IA string theory contains only closed strings. It is non-chiral, meaning it treats left and right equally. This makes it simpler in some ways, but also means it cannot directly produce the chiral, or handed, nature of the weak nuclear force that we observe in our universe. Type IB string theory also contains only closed strings, but unlike type IA, it is chiral. It has a rich mathematical structure that makes it particularly useful for certain theoretical calculations. Heterotic SO string theory is a hybrid. It combines elements of the 26-dimensional bosonic string theory for left-moving vibrations with elements of the 10-dimensional superstring theory for right-moving vibrations. This might sound impossible, but mathematically it is perfectly consistent. It has the gauge symmetry so. Heterotic E8 times E8 string theory is similar to the SO heterotic theory, but with a different gauge symmetry group. E8 times E8. This theory was particularly exciting because the E8 times E8 symmetry group is large enough to contain the symmetry groups of the standard model. This meant that, at least in principle, heterotic E8 times E8 could potentially reproduce the particles and forces that we actually observe. Now, here is the problem that 5 theories created. String theory was supposed to be the theory of everything, the unique final theory that describes all of nature. But if there are 5 different versions, which one is the real theory of everything? Having 5 candidates is embarrassing for a theory that is supposed to be unique. It is like claiming you have found the one true map of reality and then discovering that you actually have 5 different maps that do not agree with each other. This puzzle hung over string theory for about a decade. Physicists made enormous progress on each of the 5 theories individually, discovering deep mathematical structures and surprising physical predictions. But the question of which theory was the right one, or how the 5 theories were related, remained unanswered. The answer came in 1995 in what is now called the Second Superstring Revolution. And it came from Edward Witten. In February of 1995, Witten gave a talk at the Strings Conference at the University of Southern California that sent shockwaves through the physics community. He proposed that all 5 superstring theories, which seemed so different from each other, were actually not 5 separate theories at all. They were 5 different limits, 5 different corners of a single deeper theory that lived in 11 dimensions rather than 10. Witten called this deeper theory M theory. When people asked what the M stood for, he was deliberately vague, suggesting it could stand for master, mother, membrane, mystery, or magic. The ambiguity was intentional because M theory was not yet fully understood. It was more of a framework, a set of clues about what the ultimate theory might look like, rather than a complete theory in its own right. The key insight was the concept of dualities, precise mathematical equivalences between theories that look completely different on the surface. Witten and others showed that the 5 superstring theories were connected by a web of dualities. T-duality connects 2 theories that are compactified on circles of different sizes. If you take one theory and curl up one of its extra dimensions into a circle of radius r, you get exactly the same physics as taking a different theory and curling up a dimension into a circle of radius 1 over r. Small and large are equivalent. This connects type Ia and type Ib, and also connects the 2 heterotic theories. S-duality connects a theory at strong coupling, where the interactions are very strong, to a different theory at weak coupling, where the interactions are very weak. This connects type 1 to heterotic SO, and it means that the strong coupling behavior of one theory is described by the weak coupling behavior of another. These dualities are not approximations. They are exact equivalences. 2 theories connected by a duality are not merely similar. They are the same theory described in different languages. What Witten showed was that when you follow these dualities to their logical conclusion, all 5 theories emerge as different limits of a single underlying theory. And this underlying theory has one more dimension than the superstring theories. It lives in 11 dimensions. Why 11? Because there was already a theory in 11 dimensions that had been studied since the 1970s. 11-dimensional supergravity. Supergravity is a theory that combines supersymmetry with general relativity. In the 1970s and early 80s, 11-dimensional supergravity was considered a promising candidate for a theory of everything, but interest faded when it was shown to have problems at the quantum level. Witten's insight was that 11-dimensional supergravity is actually the low energy limit of M-theory, just as each of the 5 superstring theories is a different limit of M-theory. M-theory also introduced a fundamentally new type of object into the picture. String theory, as the name suggests, is built on strings, one-dimensional objects. But M-theory contains not just strings, but also higher-dimensional objects called branes. A brane is a generalization of a string to higher dimensions. A zero-dimensional brane is a point particle. A one-dimensional brane is a string. A two-dimensional brane is a membrane, like a sheet or a soap film. A three-dimensional brane is a three-dimensional volume. And so on, up to 9-dimensional branes. Branes play a crucial role in M-theory. Strings can end on branes, which means that the endpoints of open strings are attached to branes. The interactions between strings and branes give rise to gauge fields, similar to the gauge fields of the Standard Model. And here is something truly mind-bending. It is possible that our entire observable universe is a three-dimensional brane, a three-brane, floating in a higher dimensional space called the bulk. All the particles and forces of the Standard Model, which are described by open strings, would be confined to our brane. But gravity, which is described by closed strings, would be free to travel through the bulk. This could explain why gravity is so much weaker than the other forces. It is not that gravity is intrinsically weak, it is that gravity spreads out into extra dimensions that the other forces cannot access. The gravitational force we feel is just a tiny fraction of the total gravitational force, most of which has leaked into the bulk. This picture, known as the brane world scenario, was developed in detail by Lisa Randall and Raman Sundram in 1999, and it has testable consequences. If our universe is a brane in a higher dimensional bulk, then at very high energies, we might be able to see signatures of the extra dimensions. Particles might temporarily leave our brane and travel through the bulk, appearing as missing energy in particle collider experiments. Gravity might behave differently at very short distances, deviating from Newton's inverse square law. These predictions are, in principle, testable, and experimentalists have been searching for these signatures. The M-theory picture is breathtaking in its scope and ambition. It proposes that all the fundamental forces and particles of nature, including gravity, arise from a single 11-dimensional theory containing strings and branes of various dimensions. The 5 superstring theories that were previously thought to be separate are just different windows into this one deeper reality. And the apparent 4-dimensional universe that we observe is just a brane floating in a higher dimensional space-time. But M-theory, for all its elegance, has a serious problem. We do not actually know what it is. We have a collection of clues, a set of limiting cases, a web of dualities. But we do not have the fundamental equations of M-theory. We do not have a complete mathematical formulation. We know what M-theory looks like in various corners, but we do not know what it looks like in the center. It is as if we have found the pieces of a jigsaw puzzle scattered around the edges, and we can see that they fit together beautifully. But the central piece, the one that would reveal the full picture, is missing. This is one of the deepest challenges in theoretical physics today. Finding the complete formulation of M-theory might require entirely new mathematical tools, concepts that have not been invented yet. Some physicists believe that understanding M-theory will require a revolution in mathematics comparable to the invention of calculus. Now I want to tell you about what is arguably the most important development in string theory since M-theory itself. It is called the AD-S-CFT correspondence, and it was discovered in 1997 by Juan Maldacena, then a young Argentine physicist at Harvard. To explain what Maldacena discovered, I need to introduce a concept that might sound abstract but is actually profoundly important. It is called the holographic principle, and it originated from thinking about black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking made a remarkable discovery about black holes. They found that a black hole has entropy, a measure of the amount of disorder or information contained in the black hole. And the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon, the boundary beyond which nothing can escape. This was deeply surprising. For any ordinary physical system, the entropy is proportional to the volume. A room full of gas has entropy proportional to the volume of the room. But a black hole has entropy proportional to its surface area. This led Gerard Hooft and Leonard Susskind to propose the holographic principle, the idea that all the information contained in a region of space can be described by a theory living on the boundary of that region. Just as a hologram is a two-dimensional film that encodes three-dimensional information, the universe might be a kind of hologram, with all the information about the three-dimensional interior encoded on a two-dimensional boundary. This sounds wildly speculative, but Maldacena turned it into a precise mathematical statement. He considered a specific type of spacetime called anti-de Sitter space, or AD-S. Anti-de Sitter space is a spacetime with a negative cosmological constant, which means it has a kind of negative curvature. It is not like our universe, which has a positive cosmological constant. But it is a perfectly valid solution of Einstein's equations and is mathematically very tractable. What Maldacena showed is that a theory of quantum gravity in anti-de Sitter space, specifically a string theory or M-theory in AD-S, is exactly and completely equivalent to a quantum field theory, without gravity living on the boundary of that space. The boundary theory is a conformal field theory, or CFT, which is a quantum field theory with a special scaling symmetry. This equivalence is known as the AD-S/CFT correspondence, or the gauge/gravity duality. And the word equivalence is key. These are not two theories that are merely similar, or approximately the same in some limit. They are exactly the same theory, described in two completely different languages. Everything that happens in the gravitational theory in the interior has a precise counterpart in the non-gravitational theory on the boundary, and vice versa. Let me give you an analogy to help you grasp how radical this is. Imagine a room. Everything that happens inside the room, every movement of every object, every interaction, every physical process, is completely and exactly encoded on the walls of the room. If you knew everything about what was happening on the walls, you could reconstruct everything happening in the interior, with no loss of information. The three-dimensional interior is a kind of projection or hologram of the two-dimensional boundary. Now, this is not just a vague philosophical idea. It is a precise mathematical correspondence that has been checked in thousands of calculations. You can compute something in the gravitational theory and something in the boundary field theory, and the answers match exactly. It is one of the most thoroughly tested theoretical results in the history of physics. The implications of AD-S/CFT are staggering. First, it provides a definition of quantum gravity. One of the biggest problems with quantum gravity is that we do not even know how to define it properly. The calculations produce infinities and ambiguities that are hard to resolve. But ADS-CF says that quantum gravity in anti-de Sitter space is defined by the boundary conformal field theory, which is a perfectly well-defined quantum theory. It is a theory without gravity, and we know how to handle such theories. So ADS-CFT provides a backdoor into quantum gravity, allowing us to study it using tools that we already understand. Second, ADS-CFT has provided deep insights into the nature of spacetime. It suggests that spacetime is not fundamental but emergent. The boundary theory has no gravity and no extra dimensions. The gravitational spacetime in the interior, with its extra dimensions and curved geometry, emerges from the patterns of quantum entanglement in the boundary theory. When particles on the boundary are entangled, they create the geometry of the interior. More entanglement means more spacetime. Less entanglement means less spacetime. Spacetime literally emerges from quantum information. This idea was made more precise by the Ryu-Takayanagi formula, discovered in 2006 by Shinsei Ryu and Tadashi Takayanagi. They showed that the entanglement entropy of a region in the boundary theory is proportional to the area of a minimal surface in the bulk gravitational theory. This beautifully connects quantum information, geometry, and gravity, and it provides a concrete realization of the holographic principle. Third, ADS-CFT has had practical applications far beyond quantum gravity. It has been used to study the quark-gluon plasma created in heavy ion collisions at the relativistic heavy ion collider. The quark-gluon plasma is a state of matter where quarks and gluons are no longer confined inside protons and neutrons, but form a freely flowing liquid. Calculating the properties of this liquid directly is extremely difficult, because the strong force is very strong at these energies, making the standard calculation techniques of quantum field theory unreliable. But using ADS-CFT, physicists can map the problem to a gravitational calculation, which is much easier to solve. The results agree remarkably well with experimental data. ADS-CFT has also been applied to condensed matter physics, the study of materials and their properties. Certain exotic materials, like high-temperature superconductors, have properties that are extremely difficult to calculate using conventional methods. ADS-CFT provides new tools for studying these systems, and it has led to new insights into the behavior of strongly correlated electron systems. The significance of ADS-CFT for our question, what would it take to prove string theory, is profound. On one hand, ADS-CFT is perhaps the strongest evidence that string theory's mathematical framework captures something real about the universe. The correspondence is too perfect, too precisely confirmed, to be a mere coincidence. On the other hand, ADS-CFT works in anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive cosmological constant. We live in de Sitter space, not anti-de Sitter space. So ADS-CFT, in its current form, does not directly describe our universe. This is one of the central frustrations of string theory. Its most powerful and most tested result applies to a universe that is not ours. It is as if you have a master key that opens every lock in a building except the one you actually need to get through. Extending holographic ideas to de Sitter space, the type of space our universe actually resembles, is one of the most active and important research programs in theoretical physics today. Some of the leading work in this area is being done by Andrew Strominger at Harvard and his collaborators, under the name Celestial Holography. If this program succeeds, it could provide the bridge that connects string theory's mathematical power to our actual observable universe. But as of now, This work is still in its early stages. Now, let us confront the elephant in the room. The big, uncomfortable question that hangs over everything we have discussed. Why, after more than 50 years, has string theory not been proven? What is stopping us? The most fundamental obstacle is energy. The natural energy scale of string theory is the Planck energy, which is approximately 10 to the power of 19 billion electron volts, or about 10 to the power of 19 GeV. To directly observe a vibrating string and confirm that particles are indeed tiny vibrating filaments rather than point particles, we would need to probe nature at this energy scale. How does this compare to what we can actually achieve? The Large Hadron Collider, the most powerful particle accelerator ever built, operates at energies of about 10 to the power of 4 GeV, or roughly 13,000 billion electron volts. The gap between what the LHC can do and what we would need to directly see strings is a factor of roughly 10 to the power of 15. A quadrillion. That is like comparing the height of a single bacterium to the distance from Earth to the Sun. Could we build a bigger accelerator? In principle, yes. CERN is already planning the Future Circular Collider, or FCC, which would be about 100 kilometers in circumference and would reach energies of about 100,000 billion electron volts, roughly 7 times more than the LHC. But even the FCC would still be a factor of roughly 10 to the power of 14 away from the Planck energy. To reach the Planck energy with current accelerator technology, you would need a machine roughly the size of the Milky Way galaxy. This is not an engineering problem that can be solved with better funding or better technology. It is a fundamental limitation given our current understanding of how to accelerate particles. Does this mean direct conformation of strings is forever impossible? Not necessarily. History teaches us that seemingly impossible observations become possible when entirely new technologies or methods are invented. In the 19th century, Auguste Comte famously declared that we would never know the chemical composition of the stars. Within decades, spectroscopy proved him wrong. In the early 20th century, it seemed impossible that we could ever see an atom. Now we have scanning, tunneling microscopes that can image individual atoms on a surface. Perhaps some future technology will allow us to probe the Planck scale in ways we cannot currently imagine. But with our current understanding of physics and technology, direct observation of strings is not feasible. So if we cannot directly see strings, what can we do? This is where things get interesting. Because while we cannot reach the Planck energy, string theory does make some predictions that might be testable at energies we can access. The key word is might, because these predictions often depend on details of the theory that we do not know, like the specific shape of the extra dimensions. The most prominent testable prediction of string theory is supersymmetry. As I explained earlier, string theory requires supersymmetry, the symmetry that relates bosons and fermions. If supersymmetry exists in nature, then every known particle has a heavier superpartner. The electron has a selectron. The quark has a squark. The photon has a photino. The gluon has a gluino. The Higgs boson has a Higgsino, and so on. The energies at which these superpartners appear depend on how supersymmetry is broken, because we know that supersymmetry cannot be an exact symmetry of our universe. If it were, the superpartners would have the same masses as the known particles, and we would have discovered them long ago. Supersymmetry must be broken, meaning the superpartners are heavier than the known particles. But how much heavier? String theory does not give a definitive answer. Different models of supersymmetry breaking predict different masses for the superpartners. The most popular models, developed in the 1980s and 90s, predicted that superpartners should have masses in the range of a few hundred to a few thousand billion electron volts, which is exactly the energy range that the Large Hadron Collider was designed to explore. This is why there was enormous excitement when the LHC turned on in 2008. Many physicists expected that the LHC would discover supersymmetric particles, providing strong circumstantial evidence for string theory. It did not happen. The LHC has completed 2 major runs, collecting vast amounts of data at energies up to 13,600 billion electron volts. No supersymmetric particles have been found. None. The simplest and most natural models of supersymmetry have been ruled out. The superpartners, if they exist, are heavier than the simplest models predicted. What does this mean for string theory? It is important to be precise here. The non-discovery of supersymmetry at the LHC does not disprove string theory. String theory requires supersymmetry, but it does not specify the energy scale at which supersymmetry becomes manifest. The superpartners could be heavier than what the LH can produce. They might require a more powerful collider, or they might be at energies that no accelerator could ever reach. But the non-discovery is a blow. The simplest versions of string theory, the ones that would have been easiest to test, predicted superpartners at LHC energies. Those versions are now ruled out. The surviving versions of string theory require some degree of fine-tuning to explain why the superpartners are so heavy, and this fine-tuning is exactly the kind of thing that supersymmetry was supposed to avoid. It is not a fatal blow, but it is not good news either. Think of it this way. Imagine you are looking for your lost car keys. Your best guess is that you dropped them somewhere near your front door. You search the entire area near your front door and do not find them. This does not prove the keys do not exist. They might be somewhere else entirely. But it does mean your best guess about where to look was wrong, and you now have a much larger area to search with no clear idea of where to start. The LHC also searched for evidence of extra dimensions. In some models, the extra dimensions predicted by string theory could be relatively large enough that their effects would be visible at LHC energies. Specifically, if extra dimensions are large, gravity could become stronger at short distances than Newton's law predicts. And this could lead to the production of microscopic black holes in particle collisions, or to the appearance of Kaluza-Klein particles, heavier copies of known particles whose extra mass comes from momentum in the extra dimensions. Again, the LHC found nothing. No microscopic black holes, no Kaluza-Klein particles, no signs of extra dimensions. The extra dimensions, if they exist, are smaller than the LHC can probe. So collider experiments, at least with current technology, have not been able to confirm string theory. But colliders are not the only tool in the physicist's arsenal. There are other ways to search for evidence of string theory, and some of these are genuinely promising. One of the most exciting avenues is cosmology, the study of the universe as a whole. The universe is, in a sense, the ultimate physics laboratory. Conditions in the early universe were far more extreme than anything we can create in a laboratory, and the universe has left behind fossils of those extreme conditions that we can observe today. The most important of these fossils is the cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, light that was emitted when the universe was about 380,000 years old and has been traveling through space ever since. It fills the universe in every direction and has a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. The CMB is remarkably uniform, the same temperature in every direction to about 1 part in 100,000. But those tiny fluctuations, those tiny differences in temperature from one direction to another, contain an enormous amount of information about the early universe. The pattern of fluctuations in the CMB is determined by the physics of the early universe, including the process of cosmic inflation. Inflation is the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid expansion, doubling in size at least 60 or 70 times in a period of roughly 10 to the minus 36 seconds. Inflation explains why the universe is so uniform, why the CMB has nearly the same temperature in every direction. It also explains the origin of the fluctuations. During inflation, quantum fluctuations in the inflaton field, the field that drives inflation, were stretched to enormous scales by the rapid expansion. These quantum fluctuations became the seeds of all the structure in the universe. The galaxies, galaxy clusters, and cosmic web that we observe today. String theory provides specific models of inflation, and different models make different predictions for the properties of the CMB fluctuations. One key property is the spectral index, which describes how the fluctuations vary with scale. Current observations from the Planck satellite give a spectral index of about 0.965, which is consistent with many models of inflation, including some string theory models. But it is not unique to string theory. Many different inflationary models, including models with no connection to string theory, also predict this value. A more distinctive prediction involves gravitational waves from inflation. During inflation, quantum fluctuations in the gravitational field produced gravitational waves, ripples in spacetime that have been propagating through the universe ever since. These primordial gravitational waves would leave a specific pattern in the CMB called B-mode polarization. The amplitude of these gravitational waves is characterized by a number called the tensor-to-scalar ratio, denoted by R. Different models of inflation predict different values of R, and some classes of string theory inflation models make specific predictions. For example, large field inflation models, which are natural in certain string theory constructions, predict a relatively large value of R, possibly detectable by current or near-future experiments. Small field inflation models, which arise in other string theory constructions, predict a much smaller value of R, possibly too small to ever detect. Current experiments like BICEP and the Keck array at the South Pole have placed an upper limit on R of about 0.03. Future experiments like CMBS-4, a next-generation ground-based CMB experiment, and Lightbird, a Japanese satellite, will push this limit down significantly, potentially to values as small as 0.001. If B-mode polarization is detected, the measured value of R could help discriminate between different string theory inflation models and other approaches. But I want to be honest with you. Even a detection of B-mode polarization would not uniquely confirm string theory. It would confirm inflation, and some inflation models are inspired by string theory. But the link between the observation and string theory specifically would be indirect. It would be a clue, not a proof. Another cosmological avenue involves cosmic strings. And I need to be very careful here, because the terminology is confusing. Cosmic strings are not the same thing as the fundamental strings of string theory. Cosmic strings are topological defects, one-dimensional structures of concentrated energy that could have formed during phase transitions in the early universe, much like cracks that form in ice when water freezes. They are macroscopic objects, possibly stretching across the entire observable universe. with an enormous amount of energy per unit length. However, some models of string theory predict that fundamental strings, or D-strings, a type of brane, could have been stretched to cosmic scales during inflation. These would be cosmic-sized fundamental strings, and they would behave similarly to the topological cosmic strings predicted by field theory, but with some distinctive differences. For example, the probability that two cosmic strings reconnect when they cross depends on whether they are topological strings or fundamental strings. For topological strings, the reconnection probability is very close to 1. For fundamental strings, it can be significantly less than 1. Networks of cosmic strings would produce a specific signature in gravitational waves, a background hum of gravitational waves at very low frequencies. Pulsar timing arrays, which use the incredibly precise timing of rapidly rotating neutron stars as a gravitational wave detector, are sensitive to these frequencies. In fact, in 2023, the Nanograv collaboration announced strong evidence for a gravitational wave background at nanohertz frequencies. While this signal is most likely caused by merging supermassive black hole binaries, some physicists have suggested that cosmic strings could contribute to the signal. Future, more sensitive pulsar timing arrays and future gravitational wave detectors could potentially distinguish between these possibilities. If cosmic strings of the fundamental type were detected, with a reconnection probability significantly less than 1, it would be strong evidence for string theory. But we are still far from making such a detection. Speaking of gravitational waves, let me tell you about another exciting possibility. The Laser Interferometer Space Antenna, or LISA, is a European Space Agency mission that is planned for launch in the mid-2030s. LISA will be a gravitational wave detector in space, consisting of 3 spacecraft separated by 2.5 million kilometers, forming a giant triangle. LISA will be sensitive to gravitational waves at frequencies much lower than what ground-based detectors like LIGO can detect. LISA could potentially test string theory in several ways. First, it could detect the gravitational wave signature of cosmic strings, as I mentioned. Second, some string theory models predict that extra dimensions modify the gravitational wave signals from merging black holes in subtle but detectable ways. If gravity can leak into extra dimensions, the gravitational wave signal would carry a distinctive imprint of those extra dimensions. Third, LISA could detect gravitational waves from exotic objects predicted by string theory, such as boson explosions from bosonic stars or signals from string-theoretic phase transitions in the early universe. Now let me tell you about one of the most remarkable achievements of string theory, one that even the fiercest critics acknowledge is impressive. It is the microscopic calculation of black hole entropy, and it deserves a detailed explanation. I mentioned earlier that Bekenstein and Hawking showed that black holes have entropy proportional to the area of their event horizon. The formula is S equals A divided by 4 times the Planck area, where S is the entropy, A is the area of the event horizon, and the Planck area is the Planck length squared. This formula tells us how much entropy a black hole has, but it does not tell us where that entropy comes from. In ordinary thermodynamics, entropy counts the number of microscopic configurations that give rise to the same macroscopic state. For example, the entropy of a box of gas counts the number of different ways the gas molecules can be arranged while still having the same temperature, pressure, and volume. The entropy is the logarithm of this number of configurations, called microstates. So, if a black hole has entropy, it should have microstates. There should be a huge number of different microscopic configurations that all look like the same black hole from the outside. But what are these microstates? In classical general relativity, a black hole is completely described by just three numbers: its mass, its electric charge, and its angular momentum. This is the famous no-hair theorem. A black hole has no structure, no internal complexity. So where does the entropy come from? This was a deep puzzle for decades, and in 1996, Andrew Strominger and Qumran Vafa at Harvard solved it using string theory. They considered a specific type of black hole, a five-dimensional extremal black hole, which is a black hole that is as cold as possible for its given charge. They constructed this black hole in string theory using a configuration of D-branes, the extended objects on which open strings can end. They counted the number of microscopic string-theoretic configurations, the number of different ways the D-branes could be arranged that correspond to the same macroscopic black hole. And when they calculated the logarithm of this number, they got exactly the Bekenstein-Hawking formula. Not approximately, exactly, this was a triumph. For the first time, the entropy of a black hole was calculated from a microscopic theory, and the answer matched perfectly. It showed that string theory knows something deep about the internal structure of black holes, something that no other theory had been able to reveal. Since then, the Strominger-Vafa calculation has been extended to many other types of black holes, including rotating black holes, charged black holes in various dimensions, and near-extremal black holes. In every case, the string theory calculation agrees with the Bekenstein-Hawking formula. But there is a caveat, and it is an important one. The original calculation and most of the subsequent extensions apply to extremal or near-extremal black holes. These are black holes at or near zero temperature, which are not the kind of black holes that exist in our universe. Real astrophysical black holes, like the ones at the centers of galaxies, are far from extremal. Extending the microscopic entropy calculation to realistic, non-extremal astrophysical black holes remains an open challenge. Nevertheless, the fact that string theory can reproduce the Bekenstein-Hawking entropy from first principles for any class of black holes is remarkable. It suggests that string theory captures something fundamental about the quantum nature of gravity, even if we do not yet know whether it describes our specific universe. Closely related to the entropy calculation is the black hole information paradox, which is one of the deepest puzzles in all of physics. Let me explain it carefully, because the recent developments in this area are some of the most important advances in theoretical physics in the past decade, and they are directly relevant to our question about proving string theory. In 1974, Stephen Hawking made a remarkable prediction. He showed that black holes are not completely black. Due to quantum effects near the event horizon, black holes emit a faint glow of thermal radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly shrink and eventually evaporate completely. Hawking's calculation showed that the radiation is perfectly thermal, meaning it is completely random and contains no information about what fell into the black hole. This creates a paradox. Suppose you throw a book into a black hole. The information in the book, every word, every letter, is now inside the black hole. As the black hole evaporates via Hawking radiation, that information should come out. In quantum mechanics, information is never lost. This is a fundamental principle called unitarity. But if the Hawking radiation is perfectly thermal, it contains no information. When the black hole evaporates completely, The information in the book is gone. It has been destroyed. This violates one of the most fundamental principles of quantum mechanics. If information can be destroyed by black holes, then quantum mechanics as we know it is wrong. This is the black hole information paradox. For decades, physicists debated this paradox. Hawking initially believed that information was genuinely lost, that black holes destroy information and quantum mechanics must be modified. Most string theorists believed that information is preserved, that it somehow comes out in the Hawking radiation in a way that Hawking's simplified calculation could not capture. In 1997, Hawking and Kip Thorne made a famous bet with John Preskill that information is lost. In 2004, Hawking conceded the bet, saying that he now believed information is preserved. But he did not provide a clear mechanism for how the information gets out. The resolution, or at least a major step toward the resolution, came from an unexpected direction. It came from the mathematics of string theory, specifically from the tools developed in the context of ADS/CFT. In 2019, a series of remarkable papers by Jeffrey Pennington and independently by Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield showed how to calculate the entropy of the Hawking radiation correctly using tools inspired by string theory. The key concept was a new geometric construction called a quantum extremal surface, and a new contribution to the entropy calculation from regions called islands. The details are technical, but the result is stunning. When you include the island contribution, the entropy of the Hawking radiation follows a curve known as the Page curve, named after the physicist Don Page. The Page curve is what you would expect if information is preserved. The entropy of the radiation initially increases as the black hole emits more and more radiation. But at a certain point, about halfway through the evaporation process, the entropy starts to decrease. By the time the black hole has completely evaporated, the entropy of the radiation has returned to zero, meaning all the information has come out. This result was achieved using mathematical tools that are rooted in string theory, specifically in the Ryu-Takayanagi formula and its generalizations, which came from ADS-CFT. Without string theory's holographic framework, this calculation would not have been possible. Some physicists have called this the most important theoretical result of the past 25 years in quantum gravity. It does not prove that string theory describes our universe, but it demonstrates that string theory's mathematical framework is powerful enough to resolve one of the deepest paradoxes in physics. It is hard to overstate how significant this is. For decades, the black hole information paradox seemed like it might require entirely new physics to resolve, and it turned out that the tools to resolve it were already contained within string theory. But again, we must be careful. This resolution works within the context of ADS/CFT in anti-de Sitter space. Extending it to our actual universe, which is closer to de Sitter space, remains an open problem. And the resolution is theoretical, a mathematical calculation. It does not make predictions that can be tested by observing actual black holes, at least not with current technology. Now let me shift gears and talk about something that represents a genuinely new direction in the effort to test string theory. It is called the Swampland Program, and it is one of the most exciting developments in string theory in recent years. The Swampland Program was initiated by Qumran Vafa of Harvard in 2005, and it represents a fundamental shift in how physicists think about testing string theory. Instead of asking what does string theory predict, the Swampland Program asks what does string theory forbid. Here is the basic idea. In quantum field theory, the framework that underlies the Standard Model, there are many possible theories. You can write down an enormous number of different quantum field theories with different particles, different forces, and different properties. But most of these theories, it turns out, are not consistent with quantum gravity. Most of them cannot be embedded into string theory. The set of theories that are consistent with quantum gravity is called the landscape. The set of theories that look consistent on their own but are actually incompatible with quantum gravity is called the swampland. The swampland program seeks to identify the principles that distinguish the landscape from the swampland. These principles are formulated as conjectures, specific statements about what kinds of physics are and are not compatible with quantum gravity. And some of these conjectures make predictions that are testable. Let me describe some of the most important swampland conjectures. The weak gravity conjecture states that in any consistent theory of quantum gravity, gravity must be the weakest force. More precisely, for any gauge force, like electromagnetism, there must exist a particle whose charge-to-mass ratio is large enough that the electromagnetic repulsion between two such particles is stronger than their gravitational attraction. This might sound like a technical statement, but it has far-reaching consequences. It constrains the possible masses and charges of particles, and it can be checked against observations. So far, every known particle is consistent with the weak gravity conjecture. If a particle were discovered that violated it, it would be evidence against string theory. The distance conjecture states that when you move a large distance in the space of possible physical configurations, called moduli space, an infinite tower of particles becomes exponentially light. This conjecture has implications for the behavior of scalar fields, including the Higgs field and potential dark energy fields. It predicts that if dark energy is caused by a scalar field, that field cannot remain at the same value forever. It must eventually change, which means dark energy should be dynamical, changing over time. The de Sitter conjecture, which is more controversial, states that stable de Sitter space, a spacetime with a positive cosmological constant that remains constant forever, cannot exist in string theory. If this conjecture is correct, then our universe, which appears to have a positive cosmological constant, cannot be in a stable state. The dark energy must be slowly changing, and our universe must eventually transition to a different state.